Okay, so today's video is still an extension of the multivariable calculus that we're going over. Today I'm going to go over definite double derivatives. Now, just as a regular derivative allows you to find the area, just as a Cartesian um, single variable function, and its derivative allows you to find the area underneath the curve. A double derivative allows you to find the area underneath a three-dimensional curve. That function representing the curve being dictated by two different dimensions, usually x and y. So that's what we're going to go over today. I only have one practice problem because I'm recording this late at night. So sorry to disappoint. Okay, so I would like to point out that this video is over definite double integrals, meaning the bounds of our integrals are constant, they are static, and are not dependent on the value of any other variable. In a future video, I do plan on going over indefinite integrals, but that will have to wait. But nonetheless, modeled here on your video is a three-dimensional plane, and I'm going to give this plane a curve, which we'll call z. And z is going to be a function dependent on the values of x and y. Hold on, that looks awful. Okay, so z is dependent on x and y. I'm going to give this function a curve represented in this graph. It's going to be an arbitrary curve. Okay. Okay, that actually looks pretty good. You had no idea how long this has taken. But nonetheless, modeled here, we have a plane, a curve, whatever you want to call it. By taking the double integral of this curve, we're able to find the volume underneath it, just as you can find the area of a two-dimensional function. So before I explain how to find the double derivative, I'm going to explain the premise to you. This integral above has exists in two separate intervals, the y and the x. Now, for simplicity, I'm going to say that the y plane, or the y dimension of this curve, starts at starts at the origin 0 and ends right here at, I'm going to say A. As for the x interval, again, it's going to start at the origin and it's going to persist till it has reached B. Now, the intervals, of course, intercept, and we essentially have what's left of this shadow underneath that this curve projects. And so by finding the double integral, we're going to find the volume that is represented here. And so that's the point of a double integral. And I'm going to explain how we can find this. Okay, so a double integral can be found by taking your function. And note that this takes place in multiple steps. I may need to write that a bit smaller, actually. Okay. So we can begin by finding the definite or indefinite, in this instance, definite integral of this here function with respect to one of the dimensions. For the sake of this video, or at least this example, let's say dx. But as the name implies, we have to take the derivative or the integral once more, this time with respect to dy. Now, what's important to note is that, and I'm going to call the integral of z capital Z. Okay, and so that of course represents the volume given by this curve here. So what's important to note, as I've just said, is that we take the integral with respect to x of our function, and that actually yields a function that can be modeled with respect to y. And then from there, what we do is we take the integral of this function modeled with respect to y, and we take the integral of that, thereby finding the volume. So to put this into practice, I'm going to illustrate the taking of this the taking of the integral of this function. So by taking the x integral, we're actually finding a function that can represent this plane here at any point. And I'm just going to write this in a two-dimensional sense. If we have z here, sorry, if we have z here and x here, and some function, by taking the integral, which is essentially, in a sense, by taking the definite integral of this function f of x of y here, we are creating an expression with regards to y. So we are almost, at least in a two-dimensional sense, taking the indefinite integral, because we're just coming up with a function that represents the height. Or sorry, we're coming up with a function that represents the area. But we're doing it at every given point, since this returns a definite, sorry, since this returns a function that represents y. So by taking the integral and expressing it, so for taking the integral with respect to x, we are finding this plane here. And by then finding the integral with respect to y, we are really extending it this way, thereby finding all of this volume. And so that's how double integrals work. You take the integral of a function with respect to one variable, thereby giving you a function representing the area and extending it. That's the basis of double derivatives, and I would like to get into just one practice problem today. Okay, so I realized that the explanation I may have just given was a bit confusing. Hopefully this example will clear everything up. I'm going to begin by drawing a just a 3D representation of this function. And of course, I should point out that this function is the integrand of this here integral is going to, of course, represent the function. And what we were trying to do is find the volume of this function given the interval. So this representation is not going to be a good representation of the function, but that doesn't matter. I'm only drawing this so you can conceptually understand what's happening. This dimension is going to be x, this is y, this is z, which is of course the dependent variable. So let's say that the curve looks like that. Sure. Yeah, that's good enough. Okay. What's important to note, given this interval, is that the y, or sorry, given this integral, is that the y interval is from 0 to pi. That means over here, we can say that the, at least on this dimension, the y value is going to be equal to, or sorry, that should be right here. The y value is going to be equal to 0. The initial y value and the final y value is going to be equal to pi. However, on the x dimension, we begin at x equals 1 and end at x equals 3. This results in a that's a fine rectangle. That results in a rectangle. Of course, representing like the cross section of this here shape. And to begin, we of course have to find the integral with respect to y of this here function, meaning that the plane here is going to be found, or at least a function for this plane, because although we're dealing with definite integrals, a definite double integral results initially in a indefinite integral, and I'm going to explain why in a moment through example. But first, I'd like to model the zy plane, just as you know, a cross section of this here shape. One moment. Okay, so by finding the equation for this here cross section, by finding the integral of the first integral of this here function, we are able to find the cross section at any given point represented by essentially an indefinite integral, because the definite integral it returns is with respect to x. So although it's a definite integral for y, it's an indefinite integral for x. And by taking the first integral here, we're returning this cross section. And that cross section is then taken as the basis for another integral, which is being extended this way. So just wanted to reiterate that. Now I'm going to put it into practice. Okay, so I changed the function, or I changed the question slightly because I realized it is in its current state, it was beyond my understanding. But anyhow, this is the new function, and it is possible at our level. As I've said, we're first going to find the integral with respect to y of this here given above. So to begin, I'm going to find the antiderivative of z with respect to y. That is, of course, oops, hold on. I'm going to choose a bolder font. Okay, so the antiderivative of e to the power of x plus y squared with respect to y, of course, is going to be equal to e to the power of x times y plus 1/3 y cubed. Keep in mind that this is from y equals 0 to y equals pi, and so I'll throw that in now. If I have room, okay, good enough. So the antiderivative of y squared being 1/3 y cubed should be pretty intuitive. This term here, e to the power of x, and its antiderivative may not be. It may seem confusing, but remember that when dealing with multivariable calculus, the variable not in consideration should be treated as a constant. So e to the power of x might as well be 3. It doesn't matter because it's a constant in this instance. And for that reason, this definite integral with respect to y ends up being treated as an indefinite integral because it gets turned into an expression in terms of x, and I'll show that in a moment. For the time being, we just need to find this value here. So e to the power of x plus y, sorry, e to the power of x times y plus 1/3 y cubed from y equals 0 to y equals pi. In order to solve such a thing, we just have to plug in variables, or sorry, plug in values. So to begin, e to the power of x, keep in mind that this variable remains as x because the values over here, these constants, are for y. So we just plug in pi for y plus 1/3 pi cubed, which becomes 1/3 y cubed at y equals pi, which ends up being pi cubed over 3, minus e to the power of x times 0 plus 1/3 times 0 cubed. Keep in mind that these two terms are going to be 0. We're just not even going to consider them. Also, I believe I just said that we're adding that fourth term. Of course, it doesn't matter in this instance, but I should have said that we're actually subtracting it. And so this is our new value, which we're going to simplify as pi e to the power of x plus pi cubed over 3. Now, as I've just said, although this is a definite integral, we end up still with a function that has unknown variables in it. And this here represents the yz plane at any point in time. And its value is entirely dependent on x. And so that's how this works, because we're not done. This right here only represents this given. So all we have left to solve with this double derivative is the integral from 1 to 3 of pi e to the power of x plus pi cubed over 3 dx. So now we have a plane given here, and we're just extending that outwards, and that's going to give us the volume. So that's all we have yet to solve. Give me a moment as I clear this up. Okay, I switched up the color because pink was getting a bit annoying, a bit bland. But nonetheless, I'm going to continue the video with green. So we have what is essentially a regular integral because we already have taken the integral of the first of the double derivatives. And so now we just need to take our new variable, or sorry, our new function with respect to x. And so this is equal to pi to the power, pi times e to the power of x plus pi over 3 cubed x from x equals 1 to x equals 3. And hopefully I shouldn't have to explain why this is. This is just a standard equation. Sorry, rather, this is a standard Cartesian integral. There's not much that you probably haven't seen at this point. So all we have to do now is plug in our constants, x equals 0 and x equals 1 and x equals 3 into our new antiderivative, and that should give us the volume of z over this given integral. So I'm just going to do that right now. Pi times x to the power of 3 plus pi to the power of 3 over 3 times 3, and that simplifies to pi to the power of 3 minus pi to the power times e to the power of 1 minus pi cubed over 3 times 1, which of course is just pi cubed over 3. And we can, unfortunately, simplify this further. I don't really want to, but we might as well. This here I'm going to model as 3 pi cubed over 3. And so we can say that this volume is equal to pi e cubed minus pi times e plus 2 pi cubed over 3. We could take the pi out, but I find that unnecessary. This is the final volume of our equation here. Sorry, it's a bit late at night, but thank you for watching. I hope you enjoyed this. Next video should be over indefinite double derivatives.